Here in this video, we're going to tackle another trouble ticket. But in this particular troubleshooting case study, we're not told the underlying technology that needs troubleshooting. It was sort of a giveaway in the EIGRP module that we would be troubleshooting an EIGRP issue, or in the OSPF module that we would be troubleshooting an OSPF issue. But here, very generically, we're told that PC1 cannot reach this host out on the internet. This host has an IP address of 203.0.113.1, and we're unable to reach it. And this is similar to the trouble tickets you'll be tackling on the T-Sheet exam. And I want to give you a strategy for quickly isolating where the issue is. And you might notice that this topology is a bit more complex than the other topologies we've seen throughout the course. We've got multiple routers and switches, we've got OSPF in 3 different areas, we've got EIGRP, we've got BGP, we're doing route redistribution between OSPF and BGP on router R1, we're doing route redistribution between EIGRP and OSPF on router R4, we've got an ether channel between the access layer switch, ASW1, and the distribution layer switch, DSW1. We see that PC1 is in VLAN 1. And by the way, I'm using a switch to act as my PC. On the actual exam, they may have a PC simulator where you would give a command like trace RT instead of trace route. Or if you wanted to see the IP address of your PC, you might do an IP config. But here, just realize that I'm using a switch that's not doing routing. It's configured with the default gateway. The switch is my PC. And since there is so much going on in this topology, you might find it easier to download and maybe print out this topology. I've got it available for you. It's at kwtrain.com/mod12top. KWTrain, that's one of my websites for Kevin Wallace training. kwtrain.com/mod12top. That's for Module 12 topology. You can download this topology in a PDF format there, or we can just look at it on screen. But here's how I recommend we get started on the actual exam. First, I want to make sure that I'm interpreting the trouble ticket correctly. Now, my interpretation is, based on what I just told you, is that I would be unable to do a ping from PC1 to this host out on the internet, which has an IP address of 203.0.113.1. My pings are failing. All right, I think I'm correctly interpreting the issue that we need to solve. The next thing I would do on the exam is to make sure that this PC has successfully obtained an IP address from a D8CP server. If we have a D8CP server, you might have a router on the exam that's acting as a D8CP server, and on the exam you might give an IP config to see what your IP address is, to see what your default gateway is. Here, I'm going to do a show IP route because I'm using a Cisco Catalyst switch, and the output shows our default gateway is 10.1.1.1. That's my default gateway. I'll also do a show IP interface brief to see what my IP address is, and it is 10.1.1.100. I'm just confirming that this PC has an IP address and that it has a default gateway. Again, on the exam, you would probably give an IP config like you would do on a Microsoft Windows PC at a command prompt to see what your IP address is and to see what your default gateway is. Here I do have an IP address as depicted on the topology, and I see that my default gateway is 10.1.1.1. So far, so good. Everything is matching up with the topology. Now I want to see how far in the network I can get before communications breaks down. How close can I get to that host out on the internet? And here's a big point of debate. Having taught the T-Shoot course for years, I've had some debates with students about the best way to proceed at this point. Many students argue that we should do a trace route, and that's certainly an option. If we were on a PC simulator, the command would be trace RT, but here, on a Cisco Catalyst switch, it's actually trace route. We could do a trace route to this IP address that we're unable to reach, 203.0.113.1. We can do a trace route to see how many hops along the way can we get. However, I always recommend to my students that instead of using a trace route, they instead use a series of pings. You see here, I'm not getting beyond my default gateway. I'm not getting beyond DSW1. Does that mean the issue lies on DSW1? Not necessarily. Maybe DSW1 just doesn't have a route to get to this IP address. And because it has no route to get there, communication stops right there, but maybe that's not the source of the issue. I recommend that we ping the ingress interface and the egress interface on each router or each multi-layer switch, beginning with our default gateway and go as far as we can towards the destination. I'm going to begin by seeing if I can ping my default gateway. Can I ping 10.1.1.1? Yes, I can. Can I ping the egress interface on my default gateway of DSW1? If you take a look at the topology, you'll see that the IP address of the egress interface, Fast Ethernet 1/0/1, is 192.168.1.2. Can I ping that? Yes, I can. Let's now ping the ingress interface going into R4. Here's its IP address, and I can reach the ingress interface on R4. What about the egress interface on R4? Can I ping 172.16.1.2? Yes, I can. Do you see how I'm getting further in the network using pings than I did with a trace route? I think a trace route might give us a false sense of assurance sometimes. It could lead us down the wrong path when we're dealing with issues like these. I highly recommend using a series of pings instead of a trace route. Yes, it takes longer, but it doesn't take longer than being misled for a time by using the trace route command. Now, where were we? We were checking the egress interface on R4. Can I reach the ingress interface on R3? Yes, I can. Can I reach the egress interface on R3? Can we ping 10.2.2.2? Yes, I can. Can I reach the ingress interface on R2? No, I cannot. Interesting, the pings are failing at this point. I was able to get to the egress interface on R3, but I was unable to get to the ingress interface on R2. That's where I want to focus my troubleshooting efforts. I want to go look at that connection between R2 and R3. Do you see how this can be a big time saver for us? Instead of looking at a lot of configuration on ASW1 or DSW1, we're following the path. A strategy we talked about early on in the course. We're seeing how far along the path can we get towards the intended destination, and it seems to be breaking down between R2 and R3. Let's go to R3 and check things out there. First, let's see if we have a connection to R2. I can do a show CDP neighbors command, and we see that we are communicating with R2 at layer 2. CDP is a layer 2 protocol. This tells me the interface is up. I am physically connected to R2. Let's see if I have layer 3 connectivity with R2. Can I ping 10.2.2.1? That's the IP address on the other end of this serial link going to R2. Yes, I can. I've got layer 1, layer 2, and layer 3 connectivity with R2. Great. However, communication was breaking down there, so I wonder if I'm exchanging route information with R2. Let's do a show IP protocols on R3 and see how we're configured. Again, comparing this with the topology. Let's check to make sure the areas are correct. Let's make sure that we don't have a passive interface out of which we're trying to establish a neighborship. And I'm noticing under the routing for networks area of this output that we are routing for both connected networks. The areas seem to be appropriate. That looks good to me. Let's go to router R2 and let's do a show IP protocols. Am I running OSPF here? Yes, I am. Am I routing for the appropriate networks? Yes, I am. And if you check with the topology, the areas seem to be appropriate as well. That part looks good, so let's dig a bit deeper. Let's see if we've established an OSPF neighborship between R2 and R3. I'll do a show IP OSPF neighbor. Here we have an issue. I've established a neighborship with R1, 192.0.2.2. That's the router ID being used by R1, but I've not established an OSPF neighborship with R3. Interesting. Well, now that we know we're troubleshooting an OSPF neighborship issue, let's take a look at the OSPF interface configuration, remembering our discussion of things that need to match up in order for a neighborship to form. Let's do a show IP OSPF interface, and the interface that gets me to R3 is serial 0/2/0. And I'll let you take a look at the output on screen. In fact, you might want to pause the video and look at that output. And then I'm going to go to router R3 and give a similar command. Let's go over to router R3 and let's do a show IP OSPF interface. And the interface that gets us to R2 is serial 0/2/0. And again, you might want to pause the video and check things out. I'll toggle back and forth. Here's R3. Here's R2. Here's R3. Do you notice anything that might prevent a neighborship from forming? Something that has to match with OSPF is the hello interval. And I'm noticing the hello interval on R3 is set to 10 seconds, but on R2 it's set to 30 seconds. The hello interval is different. Now it's possible that somebody went in and statically configured the hello interval, but I'm noticing something else that's different. Router R2 has a non-default OSPF network type of non-broadcast. This is a point-to-point protocol link interconnecting these routers that would normally have an OSPF network type of, as we see on router R3, point-to-point. It looks like we have a statically configured OSPF network type of non-broadcast on R2, and that's not correct. Let's take a look at this interface's configuration. I'll do a show run pipe to section, and I'll specify the serial interface identifier. It's 0/2/0. And this shows us the configuration for that serial interface. And look at this. We have an IP OSPF network command that's changing the OSPF network type, and by changing the network type, that's causing the hello interval to be changed, which then causes the dead interval to be changed. And because we have mismatched timers now between R2 and R3, a neighborship is not forming. Let's fix this. Let's go into interface serial 0/2/0, and let's put this back to the default. I'll say default IP OSPF network. And this should put it back to point-to-point. Oh, great news, look at this. It says that we have just formed a neighborship. Let's confirm that. If I do a show IP OSPF neighbor command, I am now a neighbor with R1, and I am a neighbor with R3. That's different than before. Excellent. Let's go back to PC1 now and see if we have reachability to this host on the internet. Let's once again issue the ping to 203.0.113.1. Beautiful. This time it is successful. We have resolved our issue. And we resolved it fairly quickly by isolating where to focus our troubleshooting efforts. Remember, we started off by verifying that our PC had an IP address and that it had a default gateway. On the actual exam, maybe that PC is getting its IP address via D8CP. If it's not, then you've got issues to troubleshoot between the PC and the D8CP server. You might have layer 2 issues to troubleshoot. Maybe the IP helper-address command is missing from your ingress interface on your default gateway. But here, we had an IP address, we had a default gateway, and we did a series of pings, which proved more valuable than using a trace route, to follow the path, to see how close we could get to our intended destination. Things started to break down between routers R2 and R3, and we focused our efforts there. We checked connectivity at layer 1, layer 2, layer 3. Finding that we had connectivity at layer 3, we started troubleshooting the routing protocols, and we found that we had no neighborship. Then we started troubleshooting things that might prevent the neighborship from forming, and then very quickly we resolved this issue. That's how I want you to tackle an issue like this on the exam. And now that we've got the hang of things, now that we understand our general strategy from this case study number 1, let's tackle another case study. I'll see you back in the next video for case study number 2.